Good morning. In this class, we're going to discuss about the solubility of gas in a liquid. That means your gas will be actually like solute, and the liquid will be like solvent. Okay. So there are many examples of this type of solution, like seawater, river water, pond water. Like okay. So that means many actually a small amount of oxygen can dissolve in water, which actually because of which actually the aquatic life can sustain. Okay. So this is a very common example, and also in chemistry laboratory you can see that is hydrochloric acid, HCl. Okay, is actually HCl is in the gas form. Okay, actually this gas can easily dissolve in water, actually in a very high extent. Okay, that's why we store the HCl in liquid state. Okay, not liquid state, actually in solution form with water. Okay. So these are two actually examples, and now when we are talking about the solubility, then we already discussed that solubility of solid is actually depends upon some factors, like the nature of the solvent, the nature of the solute, and also pressure and temperature. Mainly temperature. Pressure is very pressure will not going to affects in large extent, because because of the compressibility of the solids and the liquid in case of the solubility of solid in liquid. Okay, but in this case actually the solubility of a gas in liquid, the temperature and pressure, mainly the pressure, okay, will going to determine in a large extent about the solubility of the gas in a liquid. Okay, so let us now discuss about in detail. First the pressure, actually how they will going to affect the solubility of a gas in a liquid. Okay, we can take an a setup like given in figure 2.1, and in that setup actually we will take some beaker or some cylinder, okay, with some piston which can be movable easily. Okay, or that means we can apply pressure from outside to move the piston inside, or we can pull out the pistons also. Okay, so inside that cylinder or the beaker we are going to have some solution. Okay, and above the solution we have some gas particles. Okay, so now we are going to check, okay, we are going to understand what about the pressure. Actually, if we apply the pressure means what? That means we are going to apply some force. Okay, force on that piston, okay, such that the piston will go inside. Okay, that means it will go inside. That means some force by area, that means the pressure will going to apply, that means on that gas particles inside that pistons, and because of this pressure on that gas particles, that gas particle also will going to apply some pressure on the surface of the solution. Okay, so if the pressure will be applied, okay, then what will going to happen? That means what about the solubility? What about the solubility of the gas particles, okay, in that liquid? Will it going to increase or decrease? Okay, let us discuss now. So actually when we apply some pressure, that means when we apply some external pressure, okay, by using the piston, or we can apply the pressure on that piston, then what will happen? The equilibrium, that means the dynamic equilibrium which was actually present in between the solution and the gas particles will be disturbed, okay, because of the external pressure. So the dynamic equilibrium will going to disturbed. Okay, so when we apply the pressure, then what will going to happen? Actually the solubility of the gas particle will going to increase. That means more gas particles can enter into the solution or into the liquid, understand, and they will again going to actually get a new equilibrium point at which the the forward rate and the backward rate will be the same. Clear? So actually after applying the pressure, they will again going to get an equilibrium, and unless and until they will going to get the new equilibrium, the actually gas particle will going to dissolve more in the liquid. So that is the main observations. Okay, now the question is why the increment of the solubility of the gas particles in the liquids occur, okay, if we apply some external pressure. So we can understand this phenomenon or this increment of the solubility by using one law, which is given by Henry. So because of actually after his name, this law is known as Henry law. Okay, so he did this experiment and he found that the solubility of a gas in a liquid is directly proportional to the pressure of the gas. That means if we increase the pressure, then the solubility of the gas particles in a liquid, okay, will going to increase. That means it is directly related. Okay, if the pressure will going to increase, then also the the solubility will increase. At the same time, actually, one scientist known as Dalton, he also gets similar types of result of this type of experiments. Okay, and he according to him, the solubility of a gas in a liquid solution is a function of the partial pressure of the gas. So that means if there are many gas particles, many different types of gas particles in that cylinder, okay, suppose oxygen is present, also nitrogen is also present, okay, also hydrogen is also present, then there will be some different types of gas particles or gas molecules are there. So the solubility of the different gas particles will going to actually depends upon the partial pressure of the gases. Okay, so I think you all know the partial pressure. Partial pressure means if there are many gas particles in a cylinder or in a setup, okay, or in a beaker or anything like that. Okay, so if many different types of gases are present, then the pressure which can be exerted by one type of gas particles are known as their partial pressure. Okay, that means the total pressure is actually equal to the addition, or actually the addition of the all the pressure which can be exerted by the different types of gas particles. That means, let's suppose the partial one container, let's suppose we have oxygen, nitrogen and also hydrogen. Okay, then the total pressure will be equal to the pressure for oxygen plus pressure for nitrogen plus pressure for hydrogen, like that. Okay, so Henry law can be stated like this. Actually his statement is actually like this: the mole fraction of gas in the solution is proportional to the partial pressure of the gas over the solution. So what do you mean by this? Actually, mole fraction is, what is mole fraction? Mole fraction is actually quantitative representation of the concentration of the solution. That means how much moles of the solutes are present in that solvent. Okay, understand? So that means mole fraction of the gas in the solution means the how much moles of the the gaseous particles are present in the solution. Okay, that number is actually proportional to the partial pressure of the gas over the solution. That means the number, or you can simply say that the concentration of the the gas particles which are inside that solution is directly proportional to the partial pressure of that gas on that solution. So in another words, we can represent the Henry's law or the Henry's statement as like this. Okay, the partial pressure of the gas in the vapor phase is proportional to the mole fraction of the gas in the solution. What is the meaning of it? Actually, the mole fraction of the gas, which is X. Okay, the mole fraction of the gas means the concentration of the gas particle inside that solution, okay, is directly related to the partial pressure of the gas. Okay, that means if you increase the pressure, then the concentration of the gas particles which are present in that solution will be increased. So simple. Okay, let us suppose the partial pressure of the gas over the solution in the vapor phase is, let's suppose it is small p. Okay, and suppose because of this partial pressure small p, X mole fraction of the gas will be present in that solution. That means the concentration of the the solution is X mole fraction. Okay, understand? So by using the Henry law, we can actually you can express this concept mathematically, like the equation 2.11, which is small p, which is the partial pressure, is equal to kHx. Actually this is this can be derived by using the Henry's law, like the X is what? X is the mole fraction. Okay, actually the mole fraction which will be present which will be present inside that solution. That means the mole fraction of the gas particles which are inside that solution is directly proportional to the pressure, partial pressure of that gas, which is small p. Okay, that means X is directly proportional to small p according to Henry law. Okay, to actually to remove the equal the proportionality sign, we have to use one constant, and that constant is actually 1 by kh. Okay, so here X is equal to 1 by kh into p, and if you cross multiply it, then it will be your equation 2.11, which is small p is equal to kh into small x. Here small p represent what? Small p will going to represent the partial pressure. So remember this point. Okay, not pressure, partial pressure. Okay, partial pressure of that particular gas particles. Okay, and here X represent the mole fractions, okay, of the gas particles which are inside that solution. Because of what? Because of that partial pressure, which is small p. That means the the X mole fraction will be present in solution, okay, because of the pressure small p. Okay, because we apply pressure, that's why the gas particle will go inside that solution, na? Otherwise it will not go. Clear? Understand? And here this kh is the proportionality constant, and this is actually known as Henry's law constant. Clear? So again we can actually here this is p is equal to kh na, so it is equation of straight line, because we can relate this equation with the equation of straight line, which is y is equal to mx plus c. Here in place of y we can write this p, that means the partial pressure. Okay, and in place of x we can write actually the that x also only, but here x is what? The mole fraction. Okay, and here kh. Okay, kh is actually your slope. Okay, slope means tan theta. Okay, so kh can be calculated by plotting this equation in a graph, like this figure 2.2. okay, so here in the y-axis they represent partial pressure of HL, and the unit here it is taken torr. Okay, and in x-axis they use the actually they represent or they use the data for mole fraction of HCl in its solution in cyclohexane. Okay, so that means the solvent is cyclohexane. So here we can get a straight line, and by using the the slope, or you can say the tan theta. Tan theta is your slope, na? Slope is equal to tan theta. I think you already know these things in your mathematics class. Okay, so slope is actually what? Tan theta. Okay, and tan theta, that means the kh can be calculated by using the slope of this graph. Okay, again this value, this kh value, okay, the constant is actually depends upon the nature of the gas, that means the nature of the solute. Okay, so here actually experimentally it is found that the value of kh is different for different the gas particles. Okay, so suppose we have two chambers. Let's suppose in one chamber we have one solution. Okay, and let's suppose we have oxygen. Okay, and in another cylinder, let's suppose we have a solution, and suppose we have some nitrogen. Okay, so if we apply the same pressure small p, then if the kh value of the nitrogen is higher than the oxygen, then what will going to happen? The solubility of the nitrogen will going to be less than the solubility of the oxygen. Why? Because you see the p is equal to what? Small p is equal to kh into small x. Okay, so actually solubility can be actually determined, or solubility can be calculated by using this small x. Actually this small x, which is actually what? The mole fraction. Mole fraction will going to tell you about the solubility. Can you give me the answer why we can calculate the solubility from small x? That means the mole fractions. What is small x? Small x is the mole fraction. Mole fraction is what? Mole fraction is actually how much amount of or you can say how much number of moles of that gas particles are present inside that solution. Okay, So if the X is high, that means what? The number of moles of the gas particle in that solution will be high. That means the solubility will be high. That means if X is high, that means solubility is high. That means the mole fraction is high, solubility is high. Understand? Clear? So now again coming back to our example here, if the pressure is same, okay, that two cylinder pressure is same, okay, and the KH value of the nitrogen is high, okay, this KH is equal to high, then the X will be low because KH into X multiply, we have to multiply KH into X to get the same value of P, okay, for both the cases. So for nitrogen the KH value is high, so X will be lower than the oxygen, because in case of oxygen KH is lower than the nitrogen. Understand? So for oxygen the X will be higher than the X of the nitrogen. That means the mole fraction present in that solution in case of oxygen will be higher than the mole fraction of the nitrogen which will be present in that solution in the fixed amount of pressure. That means same amount of pressure according to the Henry law. So this can be actually understand, or this can be you can understand this from this table also, from table 2.2. here it is given, some data of this, the KH are given here, okay, in kilobar, okay. So here nitrogen, the KH value is what, 76.48, and here oxygen is almost 34.86. that means the KH value for oxygen is lower than the nitrogen, so the solubility of oxygen is higher in water than the nitrogen. That's why actually oxygen can slightly more soluble in water, in seawater or in river water, okay. That's why the aquatic life can be sustained in because of this presence of oxygen in that in those waters, okay. Understand? Again, if you look at the the value of the KH for same the gas, let's suppose nitrogen, okay, for different temperature. So here if you look at the table, here it is shown that the KH value for nitrogen at 293 Kelvin is 76.48, and the KH value is actually going to increase to 88.84, okay, at temperature 303 Kelvin. That means when the temperature will going to increase, the KH value will also going to increase. So that means increment of the temperature will going to decrease the solubility of the that gas, because when the temperature will going to increase, then the KH value will going to increase. When the KH value will going to increase, then X, that means the mole fraction will going to decrease, that means the solubility will going to decrease. So we can say that the increment of temperature will decrease the solubility of gas in liquid. So you can even look the same explanation, or you can give the same explanation for the oxygen also. Here from the table, okay, here you can see that from the table the oxygen KH value is 34.86 at 293 Kelvin, and it will going to increase, the KH value will going to increase to 46.82 when the temperature is 303 Kelvin. So that means it is clear that the the solubility will going to decrease with increment of temperature. So it is a very interesting result, okay. That's why actually in aquatic species are actually more comfortable in cold water than warm water. So this is the main reason, okay. Now let us discuss about some applications of Henry's law, or you can say the solubility of gas particles in liquids, okay. So the first example is the soft drink, okay. So Pepsi, Coca-Cola, or you can say Sprite, okay. So we apply some external pressure to dissolve more carbon dioxide in those solution, okay. So which are not, carbon dioxide actually not good for our health, okay, carbon dioxides, because actually what we want oxygen, not carbon dioxide, okay. So that's why it is not good for us, and we apply huge amount of pressure to dissolve that carbon dioxide gas in those soft drinks, okay. So when we open the bottle, then what will, if you notice, then you will notice that some bubbles will going to evolve, or you can observe some bubbles, okay, from below the bottle to upside, okay. So this is because of the dissolved carbon dioxides which are pressurized. So this is the first example, and the second example is scuba divers. Okay, so they actually will going to face, they faced some problems, okay. If suppose they they are going to swim inside that sea or something else, okay. So they used to use what, some cylinder with some gas, okay, oxygen or nitrogen, something like that. So but inside that water the pressure is very high, okay, because the pressure is, because of that high pressure, the solubility of gas which are inhaled by them inside their body actually will going to the dissolve, or they can go into the blood more easily, okay. That means the solubility of the gas particles or nitrogens are very high inside that blood, okay. So they can easily go into the blood. So when they come up to the surface of the water, then what will going to happen? The pressure will be less in the surface. So because of the lower pressure in the surface, then what will happen? The dissolved nitrogen inside the blood will going to remove very faster rate, and because of that they will going to face some very a very dangerous situation, and that actually that situation or this condition is known as bends, okay. And this is very painful and very dangerous for life. So that's why actually what they do, they try to mix some other gases like helium also, okay, to maintain the pressure actually, because that helium cannot dissolve easily at the high pressure, okay. So that's why they combine some some ratio, that means they use some helium with nitrogen. So they try to optimize the conditions, okay, with actually optimize the gases, the percentage of gases, such that they can have less pain, okay, when they come out from the water. So hope you understand this second example. And the third example is actually opposite to that of the second example. So here actually this is observed in case of climbers, okay. So those people try to go for trekking to a high altitudes, okay. So because of the lower pressure in the higher altitudes, they will going to suffer some low concentration oxygen, because the pressure is very low. That means the oxygen cannot go into the blood easily. So that means the concentration of the oxygen inside the blood is not sufficient, okay. So that means because of this actually they will have some problems, they will going to face some problems, okay. Like they cannot think properly, okay. They cannot think clearly, or you can say, and also they will going to feel some weakness, okay. And these symptoms are well known as anoxia, okay. So these three are actually the the applications of this Henry's law, or you can say these are the the result of this the solubility of the gas particles inside a liquid, okay. So hope you understand the examples or the applications. So now coming to the effects of the temperature on the solubility of the gas particles inside a liquid, okay. So what will happen? Actually we already discussed previously that the K's value will going to increase, because if the temperature will going to increase. Additionally, we can explain the effect of temperature in that the solubility of the gas particles inside the liquid by using some thermodynamics, okay. So the main thing is that when the temperature will going to increase, the solubility of the gas particles inside a liquid will going to decrease. But why? The first reason is that one, that means the K's value, that means the K's value will going to increase when the temperature will going to increase. That's why the solubility will going to decrease. We can use that the Henry law, that means the P is equal to KH into X, okay, to explain this. And additionally we can explain the effect of temperature, that means the solubility of the gas particles in a liquid, which is decreasing with increment of temperature by using the thermodynamics. Actually what happened, Actually this this solubility or this dissolution process can be considered as like condensation process. Okay, when the condensation process occur, that means the temperature will going to release, or the energy will going to release from that system to the surroundings when condensation occur. Okay, so so please remember this point. Okay, when condensation occur, okay, that means when some ice will go, or sorry, some water will liquid water will go into the they are condensed from, that means ice from, then they must have lose some heat energy to the surrounding, then only they can go into the liquid to that solid state. Okay, so that is the condensation process. And this dissolution process of, that means the gas the entering of this gas particle inside that solution is known as dissolution process. Okay, this dissolution process is like that condensation, and during this dissolution process actually they must have release some energy. So when they release some energy, then only the dissolution process will going to be in a faster rate. Okay, that means the solubility will going to increase. That means what? The solubility of the gas particles in the liquid will going to increase when the energy from the system will going to release to the surrounding. That means they will going to release some energy to the surrounding, means what? The temperature will going to release. Okay, so that means if we cool down that system, then the process will going to be in a faster rate or in a proper rate. Understand? According to thermodynamics or according to Le-Chatelier principle. Clear? So since this process is an exothermic process, this the dissolution process, okay, so we have to decrease the temperature to get a good solubility. That means to increase the solubility of the gas in a liquid, we have to decrease the temperature. Clear? That's why if we increase the temperature, then the solubility of the gas particles inside the liquid will going to decrease. So this is the explanation according to thermodynamics. Okay, so that's why the thermodynamics chapter is very important. Okay, if you have some confusion in thermodynamics, then please go back to your higher secondary first year, all the topics. So you have to have clear all the concept of thermodynamics, then only you can understand chemistry, physics, okay, also the biology. To understand the processes, the physical processes or biological processes or organic chemistry, chemical reactions, understand, and also the physics, some physics, you have to know about the thermodynamics. So please go through and try to clear the all concept related to thermodynamics. Heat of enthalpy, gives free energy. Okay, so all the things, what is the work function, okay, what is work, what is energy, what is heat, what are the laws of thermodynamics. Okay, so try to clear the all concept. So in this class we discussed about the effect of the first, the pressure on the solubility of the gas particles in a liquid. Okay, first and we get one law which is known as Henry law, and we use that law to explain the effect of the pressure in the solubility of the gas particles inside a liquid. Okay, then we get some other concept like the rule of the nature of the gas, which actually affect the KH value. Okay, that means indirectly we can say that the solubility of gas particles also depends upon the nature of the solutes. That means the nature of the the gas particles, because it varies with that means the KH will vary with the different gases. Okay, clear? And again we discuss about the temperature relation with the solubility. Okay, that means we actually discussed we actually explain the effect of temperature on the solubility of gas particle inside a liquid. The first way is what? The KH, that means the KH value will going to increase for a specific gas particles with the increment of temperature. We have that table. Okay, and in the table actually we have the value, and by using that value and the Henry law we can explain that. Okay, then the second explanation is your thermodynamic explanation. Okay, so hope you understand all these concepts, and I think for now or for today it is I think these are enough. Okay, so so next time we're going to discuss some other topics. Okay, so thank you.